This lecture is going to look at duality, but it's going to look at the economic interpretation of the dual. We played with the dual a little bit. Now we're going to look at some of the economic interpretations of what some of the numbers in the dual mean. First off, just for a little bit of notation, and we will use this notation or very similar notation in some other parts of this course as well. When we're going to be working for now with a primal that looks like this, and that being its dual. Now note that when you have it written like this, we have in our constraint, our coefficient in the constraint, our AIs. We have that they are less than or equal to our BIs. And we have our CIs or CJs in the objective function for the primal. When you're dealing with the dual, you're especially dealing with a transpose. So your coefficient matrix, which are the AIs, in the dual, it's AJI, so it's the transpose. Okay, so if you think about it in terms of putting it into the tableau, in one, you're dealing with this AIJ matrix. In the dual, you're dealing with the AJI matrix, which is the transpose of what you started with. So we're going to talk about what the numbers kind of mean when you're dealing with the dual. We talked about it a little bit with the primal especially in terms of our sensitivity analysis. But now we're going to look at the dual and how it's related. So when we're dealing with this kind of problem, we can view this as a resource allocation model. So what we're trying to do is we're trying to maximize profits where we have a limitation on our resources. The coefficient Cj that is in our objective function, that is the profit you can get from that product or that activity. So if you had 5x1 up there, it means x1, every one you build generates $5 in profit. So that's the revenue per unit for xj, for activity j. The resources have a limitation on their availability, and that's what the BI is. The AIJ in each row is how fast that resource is being consumed as you build or as you conduct activity J. So if you think about each constraint, you can think about it as first product, how fast am I consuming this resource? Plus the second product, how fast am I consuming this resource? Plus the third product, how fast am I consuming this resource? And the total, once you add all those things up, has to be no more than the B, the limit of that resource. So here's a manufacturing example. So for this section, I'm going to be giving a few word problems examples and kind of trying to interpret what some of the numbers mean in the primal and in the dual. So if you have a manufacturer producing two products with two machines, the manufacturer of each unit of product 1 uses 3 hours on machine A and 2 hours on machine B. Each unit of product 2 uses 2 hours on machine A and 3 hours on machine B. Machine A can run no more than 13 hours and B no more than 12 hours. And with these profits, we can now write this linear program. We are trying to maximize our profit, which is 300 times our first product plus 400 times our second product, subject to, well, product 1 uses 3 hours on machine A and 2 hours on machine B. Product 2 uses 2 hours on machine A and 3 hours on machine B. Right, I have the wrong coefficients on there. Machine A has no more than 13 hours and machine B has no more than 12 hours. So we can quickly write down our linear program with that. When you take this and you solve it, you get 3 units of product 1 and 2 units of product 2. That's our optimum. Okay? So keeping in mind that the answer is x1 equals 3 and x2 is 2. Now, let's take a look at the dual for this. At one of the things about our product or our dual that we said was that if you take any feasible point in your primal and any feasible point in your dual, the objective function value at that point in your primal will always be less than or equal to the value of the dual objective function. But when it's optimal, they're equal. So at any point, your z, which is your primal value, is always going to be less than or equal to any point for your dual. But when it's optimal, you have the equality. And what's that equal to? Your primal is equal to that, and your dual is equal to the sum of the bi yi's. They are equal. In the primal problem, the bi, the thing on the right-hand side, in your constraints, was the availability of resources. So what does this imply? If you take this equality, you have that your z, which is your profit, is equal to the sum of the biyi's, which is the optimal equation, the objective function from your dual. But the bi is the units of resource I that are available. So if you think about it, this also gives you the cost per unit of resource I. This value we've seen is called the dual price or the shadow price. We already saw this. We can think of it as the value per unit of a resource. So in the previous example, we had machine A had a limit of, I believe, 12 hours. This equation tells us that we have 12 hours available. That's my BI. YI at the optimum point is going to be the value per unit of that resource. That is our shadow price. So it is getting at the value of the resource. And this is pretty much the same slide. So let's look at the constraints. Economic interpretation of the dual constraints. Now, recall that the AIJ is the usage per resource per unit production. Okay, so think about this. Every unit production has a usage rate. That's what the AIs are. So that's our constraints. Recall that the CJs from our objective function of the primal, that's the profit from the production of that one item. So the AIJ is the resource cost for that item in a given resource. The CIJ is the profit off of that item. So now we can start to interpret, if you think about it in this way, you get a similar interpretation, that you interpret the YIs as the cost per unit of resource of that resource for that line. So with this, if you think about this observation, you can see that what the dual program is trying to get at is minimizing the cost of operation where you have a given profit for each product. Because remember that CJ, when you're from the primal, the CJ is giving you the profit per item. In the dual, that's your lower bound. So it is saying that the resources, the cost of operation for that item is always going to be larger than or equal to the profit. What you are trying to do at equality is to bring those things together. The dual is saying we want to minimize the cost of operation for that product, but it is always going to be bigger than the profit. So here's our manufacturing example again. And with this is the same answer. So 3 units of product 1 and 2 units of product 2 for a total profit. What about the dual? Well, in the primal, you're saying we want to maximize the profit given these limitations. If I were to write out the problem for the dual, it would look something like this. So somebody is planning to make an offer to the manufacturer to rent the machines to produce the same products. And they need to calculate how much to offer the manufacturer per hour of time on each machine. As you see here, we're starting to write out the idea that the dual is getting at not the profits, but the cost of the resources. So how much would you have to offer to ensure that the manufacturer would make at least the same profit while minimizing their own costs? That is what the dual problem is asking. And the answer is going to be $20 per hour for machine 1 and $120 per hour for machine 2. So in other words, that machine 1, every hour on that machine is worth $20. Every hour on machine 2 is worth $120 to the first manufacturer. That's your shadow costs. So let's try to look at another problem. So we have a diet that you're preparing a diet consisting of a couple of foods. Each food has so much proteins, fat, and carbohydrates. At the end of the day, you need to have a total amount of fat, protein, and carbohydrates, and you want to create this diet for the least cost. So what are you doing here? Your primal problem this time is a minimization problem. You are minimizing cost where you have to meet certain requirements. What about the dual? So the dual is coming at the problem from a different way. It is saying that the previous one was trying to minimize costs. This one is trying to maximize profits. And when you know how much is the amount that's being spent on the different foods, you can say, how can you maximize the profit where you have the given requirements? So again, it turns the problem on its head again by saying that instead of trying to maximize profits to meet a requirement, instead of trying to minimize costs and meet a certain requirement, you're saying, okay, well, that requirement has to be met. What is the strategy for minimizing costs or for maximizing profit? and what is it for each of those products. What is the contribution? The primal is getting at what is the contribution of each of those profits. An oil refinery, another example here. So you have two different processes available, each of which produces three types of gasoline. You have the number of gallons produced per hour as well as the cost per hour. There's requirements for deliver certain amounts. What is the optimum number of hours for each profit or for each process? So what you're trying to optimize here is you'll be trying to minimize the cost, the overall cost of the operation to deliver what you need. The dual, again, kind of turns it around. We're saying, how much does it cost to produce a unit of each type of fuel? And how can you calculate the expense for refining the fuel? So again, it's turning it around a little bit. Instead of minimizing the profits, you're trying to figure out what is the value of each of those processes. Okay, this is a section that is a little hard to get your head around. It's hard for me to explain it with these problems. The book gives some more examples. It's challenging, but it's worth it to try get your head around how to kind of interpret what the dual is saying as opposed to what the primal is saying. And how the shadow prices from the solution to the primal, actually mean something to the dual, and it can be interpreted in terms of what's the value of that resource, and is it worth spending to increase it or decrease it, or what is it worth if I try to sell off some of those resource availabilities? Questions like that. Okay.